it's inaccurate because it doesn't really show the shape. You see what I mean? So sometimes they'll ask you to analyze models like this. Okay. Another coordination number of 4 would be the ammonia molecule, Nh3. And we know ammonia from all of our work on acids and bases. Nh3 is a base. And do you remember why it's a base?
Because it can take another hydrogen.
It can take a hydrogen, but why? Yeah, it's all about that lone pair that's on the end. That lone pair is a little negative cloud on the nitrogen, and hydrogen atoms will just jump in and grab those things. So yeah, that's very attractive for a hydrogen ion. But what is the shape of the ammonia molecule? What? It is, yes. We have a coordination number of 4, and this is the standard shape for coordination number 4. But in the case of ammonia, one of those orbitals is occupied by a lone pair of electrons, not an atom. Right there. So we have the N and the 3 hydrogens. I'll just take this thing out. But we know that it's there. That's a pair of electrons not bonding to anything. What's the shape? This is a pyramid shape. The last 2 hours, I had people saying, well, it's a trigonal planar. Oh, no, they're not all on the same plane. That N is raised up. Why is the N higher than the 3 H's? Because of that lone pair pushing down the other H's, they're repelling, and that does contribute to the shape. You don't count the lone pair in the shape, but it's contributing to it. If there weren't the lone pair up there on the top, then it would flatten out. It would be a trigonal planar. But it does repel. So here's our model for the ammonia molecule, and you can see that it's got. Here's our pair of electrons pushing down those other ones. So the shape is, not only can we call it a pyramid, we have to call it a trigonal pyramid, because we're going to see another pyramid later on. So it's trigonal pyramid. Bond angle?
107.5.
Yeah, it's about, we just normally call it 107. This is a very famous angle, so we use a 0.5 in there. But with the ammonia molecule, people tend to just say 107 degrees. And again, the reason for that is because of the presence of the lone pair. That does spread out some. It takes up more space than a bonded pair of electrons does. When I see this model, I don't know why. I know why. It's the color of it, I think. It makes me think of that old cartoon when you watch it when you're younger. Oswald. You remember Oswald, the octopus?
Oh,
wore a hat. You know, he's got those short little legs. I think of Oswald when I see that model.
You know Oswald?
You never saw Oswald?
It's so sad.
Oh, it was great. I love that show. Watch it with my kids.
Oswald the octopus.
He was an octopus.
I don't know Oswald.
Yeah.
We're from Canada here, so.
Oh my god.
I was from Texas.
Well, he lived in Texas for a bit. He's on the ranch, you know.
Seriously?
No, I know.
Okay, so we have one more shape within the coordination number of 4, and that's an example of that would be the water molecule. Well, we are all very comfortable with the water molecule. 2 lone pairs and 2 bonded atoms. That's why it has a coordination number of 4, is because you got the 2 atoms bonded, 2 lone pairs. 4 orbitals are all repelling each other. So now, if it's a coordination number of 4, the base shape is the tetrahedral, but 2 of those orbitals are taken up by lone pairs. What does that leave us with when we have a coordination number of 4, but 2 of them are lone pairs? That bent. Because of those 2 lone pairs, the water molecule is bent. If those lone pairs weren't there, it would be a straight molecule. So yeah, of course, we know that. The angle of the water molecule?
90?
No, stop with the 90.
105.
Or any?
105. since we have two lone pairs, we're going to have double the 2-degree squeeze. And yeah, the angle of the water molecule is well known to be 105 degrees. Yes. Yes, they are. So keep guessing.
I got two. Get it eventually. Before or after lunch?
Probably after.
I think after. Well, these are the shapes that you learned in Chem 1.
Yeah.
Unless you had Mr. JB, who
All the way.
he went all the way. When you do the exercises that involve shape in the homework, I know that when it's crunch time, you do the path of least resistance and just try to memorize everything because you don't have enough time. But if you have the chance to, when you're doing the homework in this chapter, try to think through what the shapes are by visualizing and thinking about what the coordination numbers are and how the lone pairs will cause the others to get pushed out and repel. Not just memorizing. I do think it'll really help you to understand the shapes if you can kind of think your way through it. Now it's 10:54. Let's do one more shape, and that's going to get us to the next coordination number. Coordination number of 5. This is where we start getting into central atoms having more than 8 electrons around. In every case, we're going to have central atoms with more than 8 electrons. So the first example we're going to have in coordination number 5 is PCl5. So doing the dot structure of this one, we're going to have P that has 5 electrons and then 5 chlorines, each having 7. So we'll need a structure that has 40 electrons. And in this case, because we have 5 Cls, we have to put all 5 Cls on the phosphorus. And that's fine. There they are. I know it looks weird because that central atom seems so loaded with atoms on it. Okay, so there we have all of our electrons. If you count them up, there are 40 electrons.
Yeah, you missed one. 5 left.
Oh, you know what? I think I put one on top of the other. See how it's kind of stretched out? Thanks, guys. How would 5 Cls arrange themselves around the phosphorus?
Pyramid.
Nope.
It's
Oh, it's Pentagonal Prism.
Pentagonal
Which
Prism.
one is it?
Oh, it's
Wait, a Pentagonal
yeah,
Prism.
it's like
It's like a base.
quadric.
The base is up.
This is our
That is
double.
shape.
Rhombus.
Dude,
90-degree rhombus, right?
Double pyramid.
It's a double pyramid kind of thing, right?
It's
It looks like you got a pyramid above and a pyramid below.
It's a quadric.
What we have a central atom. There's our phosphorus in there. A chlorine above and a chlorine below, and then 3. I call it like along the waistline, where this is the head and this is the legs, and then 3 in the waist. Where these 3 on the waistline are all on the same plane. So what's the angle of those 3 along the waistline?
linear.
The angle. Other than these 3, that, and that, and that.
120.
They're 120 degrees. 120. And then these are 180 degrees. So you got 180 degrees, and then you have 120 degrees in there. So what is the shape of this thing? You're right on it, Zane. We call this thing a trigonal bipyramid.
That's a pretty ratchet.
Which you said like a double pyramid. Yeah, we got a pyramid straight up and a pyramid straight down. A trigonal bipyramid. And we call the shape, there's 2 shapes, because along the waistline they're 120 degrees. From top to the middle is 90 degrees. So we would say the shape of this is trigonal bipyramid. And the angle is both 90 degrees and 120.
You can see that, right?
So our model, you can see the model, I think it looks better than what I have here. You can see the 3 along the waist, and then the top and the bottom. That's them. That's a trigonal bipyramid. So we'll pick this up after lunch
With what?
and tackle the rest of those shapes.
What? Oh, like a butter knife you get from the lunchline?